Welcome to The Explainer. Today, we're diving into a massive, and I mean absolutely massive paradigm shift happening right now in humanoid robotics. Look, for a decade, the raw, brute power of high-pressure cylinders completely defined the industry. We're talking about machines that could jump, do backflips, and literally survive bomb shockwaves. But humanoids have been hitting a physical ceiling. And now, the battle between hydraulic fluid and electric flux is deciding the ultimate survival of these platforms. We're actually watching industry titans entirely abandon 10 years of research, just tossing out legacy systems to embrace a totally new architecture. So let's dive right into this and see exactly how the next generation of humanoids is being engineered. Okay, picture this. It's April 16th, 2024. Boston Dynamics abruptly retires their legendary hydraulic Atlas robot. Huge news, right? But the real mystery? Just 24 hours later, they unveil a brand new successor powered entirely by electric motors. And this thing is capable of these astonishing 360-degree joint rotations. It leaves you wondering, why scrap a decade of what looked like absolute perfection practically overnight? Well, the answer comes straight from the top. Mark Reibert, the founder of Boston Dynamics, anchored this whole engineering problem in practical reality. He basically said, look, hydraulics are inherently messy. Even with endless effort and incredible innovation, high-pressure fluid systems just inherently leak. It's what they do. And when you're moving robots out of a controlled lab and into consumer-facing environments, like our factories or eventually our homes, they simply cannot be dripping oil on the floor. It's a massive safety hazard, and honestly, it's just a commercial non-starter. But hey, it's not just about the mess, is it? It's about the money. $2 million. That was the jarring manufacturing cost of a single, older generation hydraulic Atlas. This astronomical price tag was driven by the need for metal 3D printed skeletons just to house these wildly complex valve systems. Plus, you needed a professional team on standby just to handle frequent failures, like burst cylinders. Now, contrast that with modern modular electric architectures. By relying on smart supply chain integration, they are pushing manufacturing costs down to the tens of thousands of dollars. The economic gap there is just insurmountable. Section 1. The Power Density Paradox. So, this frames the heavyweight rivalry between the raw brute force of fluid power and the surgical finesse of electric flex. And the contrast in these numbers is just staggering. Traditionally, hydraulic servo systems offered way higher torque and power density. The hydraulic Atlas, it boasts a massive knee torque of 890 Newton meters. Meanwhile, a modern electric counterpart like the Unitree H1 only reaches 360 Newton meters. Legacy designs loved fluid power for its spring-like absorption. That impact resistance allowed robots like Big Dog to carry 150 kilograms across rough, snowy terrain. But raw force isn't everything anymore. As we transition to real industrial use, the critical metric is now torque per kilogram. These robots have to carry their own power source efficiently without being weighed down by massive, clunky engines. Which brings us to the real kicker, efficiency. Current industry data proves that permanent magnet electric systems just drastically outperform hydraulics, hitting 80 to 95% efficiency. On the flip side, hydraulic systems lose massive amounts of energy to fluid friction and heat transfer. You're looking at a dismal 30 to 50% efficiency. Plus, hydraulics need continuous high-pressure energy, sometimes literally relying on roaring combustion engines that sound like a lawnmower. Electric, though, it's quiet, it's clean, and it's vastly more efficient. Section 2. The hidden cost of fluid infrastructure. We really need to talk about the fundamental Achilles heel of the old robotic guard. Mobility in hydraulic robots is plagued by what engineers call parasitic weight. A hydraulic humanoid is this wildly complex, heavy ecosystem. You're dealing with 28 or more parasitic cylinders, heavy hydraulic power units, and this massive web of supporting valves. All of this infrastructure introduces rigid latency. That's the time it takes for fluid dynamics to physically respond, which is agonizingly slow compared to near-instantaneous electric sensing. Add in that severe leak risk to agility ratio we talked about earlier, and it becomes crystal clear why oil-dripping infrastructure is a total disaster for nimble general-purpose robotics. So what's the fix? Well, it's clean, modern bipedal platforms utilizing single-cable electric layouts. By transitioning to these compact electric hip gimbals, engineers completely eliminate that parasitic web of heavy hoses, manifolds, and pumps. This sleek, lightweight structure is exactly what allows the new generation of electric robots to be so incredibly agile and, importantly, so cheap to manufacture. Section 3. The Electromagnetic Evolution. Now this right here is the heart of the shift. These are the specific engineering breakthroughs that allowed the David of electric motors to finally slay the Goliath of hydraulics. And the secret sauce? It's something called axial flux topology. Let's de-jargon that for a second. For a long time, electric motors in robotic joints suffered from the geometric curse. Basically, if you shrink a standard radial motor to fit inside a robot's finger or its hip, its torque just vanishes exponentially. Axial flux topology flips the script. By switching from a conventional radial flux to a flat, axial design, engineers place the magnets at a larger effective radius. This maximizes the lever arm, pulling massive torque out of tiny, compact robotic joints. It's the same physics, just finally working in our favor. And that brings us to a really beautiful concept, proprioceptive actuation. In older robots, stiff gearboxes meant the motor couldn't actually feel the outside world. It was basically numb. But with new, low-friction, transparent actuators, the motor itself acts as the sensor. We call this force transparency. It allows a robot to naturally yield when you push it, rather than rigidly fighting against its own stiff gears. It's actually a lot like how biological muscles and tendons work, providing immediate physical feedback directly from the environment. These innovations all combine to finally break the dexterity deadlock. Let's walk through it. Step 1. Adopt that powerful axial flux topology we just talked about. Because the motor is inherently stronger now, step 2 is dropping the gear ratios dramatically, from a massive 288:1 down to just 15:1. Step 3. This achieves a quasi-direct drive system. Now, why does that matter? Well, with high gear ratios, a robot's limb hits objects with the massive, multiplied momentum of a sledgehammer, which makes delicate tasks totally impossible. Dropping the ratio makes the joints back-drivable. It stops the robot from acting like a clumsy sledgehammer and allows for incredibly delicate manipulation. When you look at these highly efficient, low-ratio electric hip joint architectures, you see these quasi-direct drive systems physically at work. By combining strong axial flux motors with these low-ratio gears, the robot can execute superfluid human-like motion. It can dynamically yield and react to the terrain instantly, without needing complex external force sensors glued to every single contact point. Section 4. Structural Optimization and Thermal Realities. Swapping out the entire power system completely rewires the robot's internal anatomy. We're seeing some totally ingenious space-saving strategies being patented right now. Advanced humanoid kinematics feature 62 total degrees of freedom, but to make room for power, engineers are actually omitting the dedicated spine pitch actuator, the motor that makes the robot bend at the belly. Instead, they just rely on an angled hip pivot to perform deep squats. That one simple omission increases the internal torso volume by 270%. That massive space is then packed with high-capacity batteries and advanced thermal management. By bypassing the old cooling bottlenecks of oil reservoirs and using active liquid cooling supplemented by passive heat dissipation, engineers can manage an extreme heat flux of over 100 watts per square centimeter. That allows these dense motors to sustain 7.5 times their rated power without melting. Section 5. The mechanical threshold of agility. So, this brings us to the climax of our explainer, the exact mechanical crossover point where the industry's future is cemented. The crucial takeaway here is understanding where each technology actually belongs. There is a specific crossover point where electric efficiency drops below hydraulic brute force. Because of that, hydraulics will absolutely survive in specialized heavy-duty military or construction roles where you need rugged durability, bomb shock resistance, and heavy debris clearing. But the sheer cost, the mess, and the complexity, that means they're going to stay highly specialized. Mass-produced electric dexterity, on the other hand, with its cheap, modular proprioceptive motors, that is the definitive passport to the era of general-purpose robotics. Electric drive is the key that will put these machines safely into our factories, and eventually right into our homes. But before we wrap up, let me leave you with a provocative thought. Could tomorrow's robots actually merge both systems? Just imagine a hybrid future of muscle-specific actuation, utilizing high-power hydraulic hips to carry massive payloads, but seamlessly combined with highly transparent electric extremities and hands for delicate precision tasks. As we watch this massive evolution unfold, it really leaves you wondering, what will the ultimate robotic blueprint of the next decade truly look like? Thank you so much for joining me on this explainer. I hope it sparked your curiosity as much as it did mine.